concepts of warfare have compelled today's Army to seek greater and greater mechanization, movement, and dispersal of combat forces. At the same time, air mobility has become more and more critical, with increasing emphasis on counterinsurgency. This means that combat units must become increasingly capable of long periods of independent operation. To function independently, these units cannot be burdened by heavy logistical support. Yet it's a sad fact of life that the greater the mechanization, the greater the consumption of petroleum fuel. The problem of supplying it to the field army may well become insurmountable unless something is done. Perhaps this point may best be emphasized by a statistic. At present, about 50% of the total tonnage required to support Army field operations consists of petroleum fuel. The inescapable conclusion is that the difficulty of maintaining fuel supplies in a combat theater may halt our ground forces far more effectively than any action taken by the enemy. Epitaph for an unsuccessful operation: out of gas. It's an epitaph that must not be written. Let us take up another problem, namely the Army's second basic need for petroleum: diesel oil to operate conventional electrical power plants. Statistic: approximately 1/8 of the petroleum fuel supplied to the field army is used to provide electrical power. Here in this large depot complex, electrical power is used to light the area, to operate laboratories and shops, as well as cranes and other equipment. Port facilities make similar demands on electric power. Electricity is also needed for such purposes as maintaining airheads, communications, surveillance, and to operate missiles. These requirements are great, and they are steadily expanding. In World War II, to place these demolished European port facilities in operation, the U.S. Army brought in portable power plants which required 800 tons of fuel per day, the equivalent of the operational demands of 16 divisions of that period. To provide electric power, the Army has long used conventional plants such as this diesel installation in West Germany. This is a conventional diesel plant that supplies electric power for our military in Korea. Like all such plants, it required the transport of a great amount of heavy equipment to construct it, and of a constant resupply of petroleum fuel that places a huge burden on shipping and aircraft cargo space. Moreover, such plants, large, immobile, and above ground, are obviously vulnerable to enemy attack, as are the fuel transporters they require. Pipelines, becoming longer under modern concepts of dispersal, are in greater danger than ever of being cut by the enemy. To provide electricity in remote areas has been even more difficult because of weather, terrain, and the great distances involved. To supply a diesel plant in Greenland with petroleum fuel has required up to 80% of the station's annual effort. Diesel floating plants, such as this used at Thule, also require an enormous fuel logistic effort. It's evident then that the Army is facing a rapidly increasing problem in its efforts to supply vital petroleum fuel to the installations and units which depend on it. Fortunately, the Army nuclear power program is well on its way toward solution of these problems. Because nuclear power plants require no petroleum, and as you shall see, may eventually create petroleum substitutes in the field, the Army's problem of supplying fuel for its mechanized forces may soon be solved. However, before we examine the future, let us see how the Army's existing nuclear power plants are helping to solve the logistic problem. You're looking at a U.S. Army nuclear power plant. The ML-1, M designating mobile, L designating low power, and 1 the first generation of its type. Its electrical output equals that of a good-sized diesel plant, yet its reactor can operate for long periods without refueling, and it's sufficiently mobile to be used in combat by a field army. It's a prototype of the Army's first mobile nuclear power plant, a major technological advance in the military application of nuclear power. Like all of the Army's nuclear power plants, its principal reason for existence is to reduce the burden of providing petroleum fuels in areas which, for military, geographical, or political reasons, are difficult and at times almost impossible to support logistically. It may be transported by ship or by rail. More important, the Army's first-generation mobile nuclear power plant is air transportable in a single standard cargo aircraft, a significant capability in any military operation. However, its primary means of transportation is by truck and standard trailer. Once in a combat theater, it's capable of long periods of independent operation, giving a field commander a plant which he can move to meet various demands for electrical power. This prototype of the ML-1 generated electricity for the first time at the National Reactor Testing Station, Idaho, in September 1962. It's a direct cycle, nitrogen-cooled system with an output of 300 to 500 kilowatts of electricity. The ML-1's nuclear core weighs only a few hundred pounds, but contains extractable energy equivalent to about 4 million pounds of gasoline. It's capable of 10,000 full power hours of operation, meaning that whether trucked or flown to a field army, a remote missile base, or an isolated radar station, the power plant will arrive with the equivalent of about a 2-year fuel supply. The Army's first mobile nuclear power plant has 2 major packages: the nuclear reactor skid and the power conversion skid. Each weighs about 15 tons. These skids are normally joined into a single package during both transport and operation. The controls and instruments are located in a control cab, which is designed to be carried on a 2.5-ton truck. Certain auxiliaries required for the operation of the power plant cannot be located in the 3 major packages. They weigh 6 tons, making a total of 38.5 tons for the 4 packages that comprise the ML-1. The ML-1 power plant is as mobile as the standard military semi-trailer which transports it. It can be placed in operation within 12 hours after it arrives at a new site. It's normally offloaded for operation, but can also be operated from its semi-trailer. The ML-1 is designed to withstand all normal environmental conditions. The reactor skid, housed within an operational shielding tank and its cover, is a weather-tight structure. The power conversion skid has removable side panels, which can be left in place to keep it weather-tight. The panels can also be swung upward to protect the equipment from rain and sand. A long control cable is provided, making it possible to locate the control cab 500 feet away from the reactor. In addition to the safety of distance, This cable makes it possible to use natural terrain features or earthworks to prevent ionizing radiations generated by the reactor from endangering operating personnel within the control cab and other personnel within the area. After a shutdown following extended full power operation, 24 hours are required for plant cool down prior to relocation. In any nuclear attack on our cities, fuel supplies, large power plants, and power lines may be knocked out. Mobile nuclear plants could be sent to operate essential facilities. However, what makes the Army's first mobile nuclear power plant a major milestone in military history is its capability to support field operations. It can be quickly delivered to any trouble area in the world where electric power must be obtained independently of local sources, to such remote places as the Congo or Vietnam. It can be made available to such units as Strike Command, shown here during a training exercise in West Berlin. The combat-ready, highly mobile force is designed to be ready to leave for any trouble spot in the world at a few hours' notice. This type of nuclear plant may be expected to play a vital role in any such future operation. In 1954, the Secretary of Defense established the Army nuclear power program to meet land-based power requirements of all three services. It's a joint program of the Department of the Army, which has responsibility for developing power conversion equipment, and of the Atomic Energy Commission, which has the responsibility for the development of nuclear reactors. The projects in the program are identified by the degree of mobility, stationary, portable, and mobile, and range of power output, low, medium, and high. Initial efforts were, of technical necessity, devoted to stationary reactors. The first to be constructed was at Fort Belvoir, Virginia. This stationary medium power plant, designated the SM-1, was dedicated in April 1957. Its reactor operated for 3 years before the 700-pound core was replaced, giving a practical demonstration of the logistical advantages of nuclear power. This plant has proved invaluable in training military operators for other nuclear reactors and has provided a wealth of developmental data. It has also continued to produce enough power to operate a small military installation. The Army nuclear power program's first operational objective was to develop stationary plants for use in remote areas where the fuel logistic problem is always serious, no matter what the political or military situation. Based on the success of the Fort Belvoir reactor, the Army's first stationary field plant was installed at Fort Greely, Alaska. Of medium power, it was designated the SM-1A. Operational since early 1962, this unit produces twice as much power as the Belvoir plant, even though both have nuclear cores of the same size. This plant now provides both electrical power and space heating for Fort Greely. Meanwhile, to meet power requirements at temporary military installations, a prefabricated portable medium power plant was manufactured and pre-tested at Dunkirk, New York, and designated the PM-2A. All modules of this portable plant can be transported by standard cargo aircraft. Shown here is the air transport of one of the major packages. Destined for Camp Century, Greenland, packages were first air and sea lifted to Thule. From Thule, the entire plant was transshipped by sleds 138 miles to Camp Century under severe environmental conditions. At Camp Century, it was quickly installed in a city under ice. Time of installation, 78 days, as compared to 2 or 3 years for a stationary plant. In operation since February 1961, this portable plant provides 1,500 kilowatts of electricity and 1 million BTU per hour of heat to melt snow for Camp Century's water supply. Thus, the power necessary to supply the needs and comforts for our troops living under the ice is always available. The continuous resupply of fuel by sled or aircraft becomes unnecessary. A second portable medium power plant was installed late in 1961 at Sundance, Wyoming, to provide electricity and space heat to a remote aircraft control and warning station. Designated the PM-1, it's contained in 16 modules which can be transported in 15 aircraft loads. With an output comparable to Fort Belvoir's SM-1, it weighs less than 1/10 as much and has a 20% longer core life. A third portable medium power plant was designed to meet the Navy's requirements for power at extremely remote McMurdo Sound, Antarctica. With all equipment pre-assembled on a minimum number of heavy skids, the plant was designed to facilitate transport and assembly during the short polar summer. Designated the PM-3A, its on-site construction time was 79 days. Installed in 1962, it helped solve a great logistic problem, since the delivery of fuel oil would be extremely difficult and costly due to the great distance, adverse weather conditions, and the problem of offloading on the ice shelf. The first high-power nuclear plant to be constructed will be a mobile floating nuclear plant mounted on a ship's hull. Designated the MH-1A, it's designed to supply electricity on call to land-based installations in combat zones and underdeveloped regions throughout the world. With an output of 10,000 kilowatts, it will operate over 2 years without significant logistic support and is expected to save 20,000 gallons of petroleum fuel per day. The Army's first mobile nuclear power plant has descended from distinguished ancestors, all of great value at remote, fixed installations. However, plants designed for fixed installations are of little use in combat theaters, where there is a need for greater and greater mobility. It was soon discovered that the much desired increase in mobility and corresponding decrease in size could be achieved by a new type of reactor utilizing a closed-cycle gas turbine. The ML-1 is the first to employ this type of equipment, giving it both mobility and compactness. One illustration of the great progress that has been achieved thus far. The Army's first nuclear power plant, the stationary SM-1 at Fort Belvoir, weighs 2,500 pounds per kilowatt, while the ML-1 weighs only 250 pounds per kilowatt. Yes, the ML-1 represents a major advance, but the future holds even greater advances. The Army nuclear power program has started development of the military compact reactor, a mobile plant with 10 times the power output of the ML-1. This 2,500 kilowatt mobile plant will need neither a long warm-up nor shutdown period, nor will it require expedient shielding of Earth to protect the personnel operating it. And for the first time, we'll have a nuclear power plant weighing considerably less than a diesel plant of comparable output. Its very designation, MM-1, is significant. This means that despite its great mobility, it will be of medium power as contrasted to the low power output of the ML-1. However, the greatest impact of this nuclear power plant on current thinking is the belief that it may lead to a major breakthrough, the solution to the problem of supplying fuel for the propulsion of military vehicles. We have seen that the core of a mobile nuclear reactor weighs only a few hundred pounds, but contains extractable heat energy equivalent to about 8 million pounds of gasoline. Problem? How can this vast reservoir of energy be used to propel vehicles? The most obvious approach is to use a nuclear power plant directly as a propulsion engine. However, the weight would be too great for ordinary combat vehicles. And very large vehicles would have serious tactical disadvantages. Difficulty of shielding against radiation and high cost would be other serious drawbacks. The problem then is to convert the energy from a nuclear plant to a form which can be conveniently dispersed and utilized in vehicles of many types. With this objective in mind, the Army nuclear power program is focusing its efforts on what has come to be known as the energy depot concept. Several approaches to this concept are technically feasible. For example, a reactor and associated equipment could be used to manufacture versatile chemical fuels from elements universally available in air and water. Or the reactor could charge reusable packages of energy comparable to extremely powerful and compact storage batteries. The packages of fuel or energy would then be distributed and utilized to propel combat vehicles. It's estimated that a single reactor core employed in a single energy depot could produce the same mileage in the supported vehicles as 2 million pounds of gasoline. With mobility equal to that of the supported combat force, such nuclear-powered energy depots could manufacture vehicular fuels within a combat theater and near the point of use. One can foresee several of these depots providing the necessary fuel for a task force in independent, continuous operation with freedom from the restrictions of the past. This means our modern machines of combat need no longer be frozen by limited supplies of fuel. One fact is certain. Nuclear power plants have progressed rapidly, but they have only begun to yield the dramatic benefits which will ultimately open new and perhaps unimagined horizons in military science.